Hello, welcome to the CH410 lecture on chapter 26, that is chromatography. So this is a series for the CH410 course, Instrumental Methods of Analysis. So what is chromatography? Chromatography basically is a process used for separation technique. And chromatography permits the separation of closely related compounds of complex mixtures. And in chromatographic separations, the samples are transported in a mobile phase and allowed to interact with the stationary phase. So those are the two major systems that operate under chromatography. The mobile phase is the carrier, and the stationary phase is fixed, where it can slow the migration of the analyte. So the overall category of chromatography can be classified into two types, and that is column chromatography, where the stationary phase is held in a narrow tube through which the mobile phase is forced under pressure. And the other is a planar chromatography, where the stationary phase is supported on a flat plate or the interstices of a paper. Here, the mobile phase moves through the stationary phase by capillary action. However, the more fundamental classification of chromatographic method is based upon the types of mobile phase and stationary phases used. And there are three categories here: the liquid chromatography, or gas liquid chromatography. That is, the liquid chromatography, where the separation based on the liquid-liquid separation, and gas chromatography, pretty much on the gas phase. And the third one is supercritical fluid chromatography. Now you'll see that in the chromatography techniques, basically the type of interaction between the mobile and stationary phase results in the different types of equilibrium. So here we're looking at a partition between gas and liquid, which is a partitioning constant type of equilibrium. And here's adsorption sort of process on the surface of a solid. And likewise, if you're looking at the liquid, here is a partitioning between the immiscible and the between the immiscible liquids. And the others down here, you will see that ion exchange is also part of the process. So here you will have the different exchange of the ions based on their charges as they go through the column. And the last one, you're looking at some of the influences based on the size exclusion, which is here is part of this size exclusion chromatography. Now, the elution process basically involves the washing of a species through a column by continuous addition of the fresh solvent. The sample is introduced at the top of the column and allowed to migrate through with the running of that mobile phase, which is what we call the eluent. So the eluent can be either operated under force of gravity or actually under the use of pump in the case of liquid chromatography, or gas pressure when we are talking about gas chromatography. Now this illustrates the movement of mixtures along a tubular column. You have the mixture A and B introduced at the top, and here this column is filled with a stationary phase, and then the elution process is allowed to run through a period of time. So beginning right from the very start at time 0, and then when it reaches the end of the column or to the detector, you will be expecting to see the separation, and that's essentially what happens. So the migration rate through this column is what will give rise to the separation out of the components. However, one other point that is important to note here, that during the course of migration you also see the broadening of these bands, which is essentially resulting in this peak broadening, as you see here in the final signal. So what we have at the end of a chromatographic analysis is a chromatogram. Chromatogram is a plot, and that plot is a plot of the either height or the area of the peak as a function of the retention times. So the position of the peaks on the time may serve as a means to identify the components of a sample, that is their retention time, and the area under the peaks provided a measure of the quantity, which is the amount of the component that is in that mixture. So here is the time line of the separation, where B and A are just beginning to separate at the initial part of the separation in the column, and as they migrated to the end of the column, you expect them to be well resolved. So this is essentially what we want to get at the end, where there is a distinction between the components and a well-resolved peaks between them. So we'll be discussing how this can be obtained and some of the physical parameters that I use in order to control them. So when we discuss the physical process, we basically want to see it in terms of the migration rates. So the effectiveness of chromatography column is in the separation of two solids depend upon the relative rates at which the two species are eluted. The rates are determined by the magnitude of the equilibrium constants. So as I mentioned from the start, the equilibrium conditions are what really is governing a lot of these processes that is taking place in the separation. So in the equilibrium constant, we are basically looking at the distribution between the mobile phase and the stationary phase of the analyte. So there are two things that really want to be seen in a chromatograph. One is the clear separation between the peaks, and also the narrowing of the chromatographic peaks. Okay, let's look at the distribution constants. You're looking at here the analyte in equilibrium between the stationary and the mobile phase. Now, what we know that this is a process that is undergoing constant change, so it may not be as ideal to consider equilibrium, but we can make it an assumption on a micro scale level when we're looking at very, very small regions within the column. You will be expecting this sort of exchange to be in equilibrium. And you can write the equilibrium constant by the ratio of the concentrations. So it'll be the concentration of the analyte in the stationary phase over the concentration of the analyte in the mobile phase. And likewise, let's look at the retention time. Retention time basically is the time taken for the analyte to reach the end of the column. And that is given by this relationship, which can be used as the measure of the average linear velocity, or the rate of migration. So here is the velocity of the rate of solid migration, which is the length of the column divided by the retention time. L is the length of the column. And the other that we can also consider is the unretained species, which is the mobile phase mostly. in this sort of analysis. And the unretained species or mobile phase is given by the length of the column divided by the retention time of the mobile phase. And the retention time of mobile phase, we know it's going to be rather short, and also it's given the term as dead time. So here the illustration to show the difference between retention time. This is from the start to where the peak of the analyte, that's a retention time. And the retention time of the mobile phase is from the start to where the mobile phase appears in the chromatogram. And so this is Tm, which is the dead time or the retained species time, retention time. And this one is the analyte retention time. So the retention time S, just a sample on its own, will be this. From here, the mobile phase retention time to the analyte's retention time. Now, one of the representation that's a lot more easier to work with in chromatography is what we call the retention factor. So the rate of migration, instead of using the equilibrium constant values, we can relate it to this term called retention factor. And retention factor is essentially the equilibrium constant or partitioning constant multiplied by the ratio of the volume. This is the ratio of the analyte in stationary phase over the ratio of the analyte in the mobile phase. When we're talking about these two ratio, this is essentially taking into account the entire volume in the column. So that can be worked out fairly easily from the thickness of the column and also the diameter of the column. So Ka is the distribution constant for the species A, and this relationship here at the top can be refined or rearranged and substituted to arrive at the retention time relationship, which is a lot more convenient when we're dealing with this measurement. So retention factor of A is essentially the retention time of the component minus that of the dead time, which is Ts, and then divided by Tm. So all this term here you can obtain from the chromatogram fairly easily when we're dealing with the retention times of the mobile phase and the analyte. Now, what is important about retention factor is that you're looking at conditions where retention factor larger than 20 or 30. When you get that value, you are not really reaching an ideal position or timing for separation, because it's going to be way too long elution times to get a chromatogram. So ideally, you're looking at something, a retention factor in the range of 2 to 10. Now, the relative migration rates can be determined from the ratio of the retention factors, and that is given by this term here, selectivity factor. So selectivity factor is essentially the ratio of two components when they are separated. It'll be the ratio of their K values, which is the distribution constant values. So Kb over Ka, where Kb is the distribution constant for species B and Ka is the distribution constant of species A. So alpha, which is the selectivity factor, is essentially the ratio, and always taken to be greater than 1. And that can be re-expressed in terms of the retention factor. As we say, we saw that how retention factor, we just looked at how that equation is arrived. It's a very convenient term in chromatography. So retention factor Kb and Ka are the retention factors, and then can be expressed in terms of the retention time values. Now, how do we describe the column efficiency? These are the two main parameters that are used for the column efficiency. One is the plate height, H, and the plate count, N. Now, plate height and plate count, the two are very much related, and we'll arrive at how that is obtained in the column. So what we have here, the number of plates, that is the plate count, essentially equal to the plate height. You divide that from the length of the column. Now how we get this height is very, very crucial, because that height is something that is not really clearly delineated in the columns, but we can make some empirical judgment on that, as we see in the slides coming. So L is the length in centimeters of the column packing. So the efficiency of the chromatographic column increases as the plate count becomes greater. So in other words, this N value, you want it to be as high as we can, and this H value to be as small as it can. So in a chromatography column, we say that it is made up of numerous discrete but contiguous narrow layers called theoretical plates. As I say, these plates here, theoretical plates, are not physically delineated or established there in each column, but we can do a simple empirical relationship and obtain some of the quantities and values of this theoretical plates. So the movement of solid down the column was then treated as a stepwise transfer of equilibrated mobile phase from one plate to the next. So here's the relationship that we will discuss. That is, H is essentially equal to the standard deviation squared. So we're looking at this value here. The sigma is the standard deviation of a peak. So if we're looking at a normal peak, you will use that, or we're going to use that. So we're going to take into account a peak that has the Gaussian type of shape, and from there we can determine the standard deviation, mean and standard deviation, and use that as part of this empirical relationship. So the plate height can be thought of as the length of the column that contains a fraction of the analyte, the length of a column that contains a fraction of the analyte that lies between L minus standard deviation and L plus standard deviation. Because the area under the normal curve bound by sigma, that is the first standard deviation, is about 68%. So this is what we get from statistics in the law of probability for within plus or minus 1 standard deviation is 68% of the total area. And the plate height is defined as defined contains approximately 38%. And you can see that 34% is half of the 68 that is mentioned in there. So this diagram here sort of illustrates the point. So if you take this to be a column, and the analyte travels through the entire length of the column, L. Now as it comes out of the column, it gives you this peak. So we are approximating that peaks to be a Gaussian curve, where this is the mean. We take the mean as L, and then we'll take the L plus 1 standard deviation and L minus. So in other words, we are using this region to be the measure of the plate height. So we say height is equal to sigma squared, which is the variance, over L. Now what we can do is improve that measure a bit more. Instead of just using half the height, we can take the shape of the triangle here, because in that way we can increase the total amount of the analyte that we are looking at. So if we do this and take into account the width and the area of the triangle, we are considering to be within 96 or 98% of the analyte in here, which is a lot better than just 68%. So using that, we come up with a relationship of N, which is a lot more better in terms of the estimation of the plate height and the plate count. So that's the estimation of N. And the plate count N and the plate height H are widely used in the literature and by instrument manufacturers as a measure of the column performance. So how does the mobile phase flow rate affect the separation? So the magnitude of the kinetic effects on column efficiency depends on the length of time the mobile phase is in contact with the stationary phase. So this process in which the mobile phase runs through the stationary phase is what we want to consider into how that flow rate is going to be changed or influencing the final outcome. So the efficiency studies have generally been carried out by determining H as a function of the mobile velocity or the mobile phase flow rate. We'll come to some of these terms a little bit more in detail, so let me just highlight a few of the symbols here. So the linear velocity is U, and that's the unit, centimeter per second. Diffusion coefficient of the mobile phase is dm. Diffusion coefficient stationary phase is ds. Retention time, retention factor, so it's k, no unit. And diameter of packing particles, dp. And the thickness of liquid coating is df. So these are the various parameters we'll be looking at when we come to some discussions here. So in general, this is basically the relationship between the plate heights, function of the mobile phase velocity. So from 0 to 1 here, and you're looking at the plate heights relationship here. So these two plots here basically give you the same trend. However, you're looking at two different scales here. The top one, which is for liquid chromatography, you see a very narrow plate heights, 0.001 to up to 0.006 here. Here is from 0.02 to 0.12. So it's a lot more higher value of plate heights in this one for gas chromatography compared to the liquid chromatography. And the two are very different. This one, you will see that even the mobile phase velocity or flow rate you're looking at in this from 0 to 1 centimeter per second compared to 0 to 100 centimeter per second. So there's a lot more rapid flow here to the gas compared to the liquid, and vice versa. You see that the plate height for the liquid is a lot more narrower compared to that of the gas. So the shape of this curve, interestingly, which is what we call the Van Dimter plots, really is governed by these three terms here in this equation. This is the Van Dimter equation. H, that's the plate height, is equal to the first one is a constant, A, and B is another constant, over U, the flow rate of the mobile phase, and C multiplied by the flow rate of the mobile phase. So rearrange this. So what are the A, B's, and C's? So A is essentially what we refer to as the flow paths. And the flow paths in a packed column, we are looking at a very wide range of flow paths. Because, you know, when a solid particle on the stationary phase is encountered by the flow of mobile phase, it has to flow around that in order to reach the or to continue with the flow. So in other words, some analytes will travel a little bit further compared to some others, depending on the random flow path they undertake. So what essentially will result in that the analyte will reach the detector in a broader sense, in a broad way. So that is what we discussed or we showed in peak broadening. Now, that also is related to the flow rate. So that's the A term. B term is the longitudinal diffusion, which is essentially the diffusion from the concentration or concentrated region of the analyte to the lesser, which goes to the edges of the boundaries of the analyte concentration, and then the mass transfer between the phases respectively, that is between the mobile phase and the stationary phase. So the Van Demeter equation contains terms linearly and inversely proportional to, as well as independent of, the mobile phase velocity. So you'll see that from the relationship that is here in the top equation. So let me just illustrate again what are the terms in there and what they relate to. A is related to the lambda term and dp. Dp is the, let me just go back to the dp here, is the diameter of the packing particles, that is the stationary phase, and that's part of the nature of the column packing. This one, the lambda term. Longitudinal diffusion is B over U, and that is related to 2 gamma multiplied by the diffusion coefficient of the mobile phase. So again, this is part of a constant based on the packing in the stationary phase. And mass transfer to and from the stationary phase, here is the CSU term. That's the migration rate velocity, as we know, and this is the mass transfer coefficient, and likewise this one is the mass transfer coefficient of the mobile phase. So the first term is the multiple path. The zone broadening arises in part from the multiple pathways, so that's one of the major contributions to the zone broadening in the chromatography. The length of these pathways may differ significantly based on the residence times in the column for molecules in the same species is variable. As I said, this sort of variation here, or the process, is called eddy diffusion. Now in the longitudinal diffusion term, that's B over U, the longitudinal diffusion is a broad broadening process as well. Solid diffuses from the center of the zone to a more dilated regions, either ahead or behind that zone. And the longitudinal diffusion is directly proportional to the mobile phase diffusion coefficient. Now these two, the mass transfer coefficient of mobile and in the mobile and stationary phase is pretty much very similar. So here it deals with the distribution constants and how they interact with the stationary phase. So these effects on the mobile phase velocity figure, in the next figure you will see how these three terms influences. Now you don't see the value of, the influence of A represented in here, because A is very much a linear relationship, and it's not as critical compared to these three here. So the B is an inverse proportionality. As you increase the mobile phase velocity, the longitudinal diffusion decreases, and the other two, the mass transfer coefficients into the mobile and stationary phase, is increasing as the mobile phase is increasing. But this sort of levels off. That is the mass transfer coefficient of the analyte in the mobile phase. So how do you reduce zone broadening? You basically look at the column. Two important controllable variables affect the column efficiency. One is the diameter of the particles making up the packing of the column, and the diameter of the column. So over the years, you've seen that columns has really undergone changes to become more narrow and yes, narrow and longer in the application of chromatography. And this in particular is seen in the capillary column gas chromatography. Now, column resolution is given by this change in Z over the width of the peaks. So whether taking the width in the full width of peak A and peak B, that is of component A and B, or half the width of the components, as you can see. And that can be related to the retention time values. So one important aspect about resolution is that a value of 1.5 represents pretty much a reliable or a very good resolution compared to values below that. So here are the terms. So delta Z is the difference between the two components, peak A and peak height of A and B, and W is the peak width, that's W, and WA over 2 or WB over 2 are the half the width. So that essentially is what we use for resolution. So in this particular bottom part, as a resolution value of 1.5, which is what we want to be seen in a chromatograph. So at 1.5, you see a clear separation when one peak drops to the baseline before going on to the other. Here you haven't really allowed this to drop to the baseline. So that RS is 1.0 and here RS is 0.75. Now in terms of the resolution, you can also see that in terms of the resolution really is a function of this K term. Of course, the plate height is plate count is in there, but this K term, what does that mean? So when we are actually doing any chromatographic separation, the parameter that is only useful for making changes into chromatograph is very manipulating or dealing with the changes in the retention factor. And where does that come in? In the retention factor in the liquid chromatography that is achieved by the changes in the concentration of the elements. So you look at this chromatograph here, in the change from 70% methanol to 30% water compared to 60% methanol to 40% methanol to 60% water. And you can see here there's hardly any resolution in the first, but if you look at the resolution here, is a lot more defined. And it happens by the changing of the concentration, the fractions of the solvents. For example, here it's a methanol water mixture. And you can see the improvement in the signal as you continue to change the ratio of the two solvents. So doing that in the liquid chromatography by the different proportion of the solvents, and that is achieved in the same way in gas chromatography, but in gas chromatography that is done by temperature programming. So here are 3 different temperature programs using gas chromatography and you can see here that the resolution a lot better in that first run. However, you suffer from a very long retention time to finish the analysis. Here is too short, and of course you also suffer from very poor resolution. There is not even any separation between 1 and 2. Here you achieve a good resolution in 3 and 4, 5 and 6, but not quite 1 and 2. So in other words, looking at this, you might have to have a compromise between a very, very lengthy chromatography analysis, or that one that you can work with, like here in the third chromatograph. So application of chromatography has grown to be a premier method for separating closely related chemical species. It can be both identified by qualitative analysis, and also it can use determination of quantities in the separation technique. In qualitative, the retention time is basically used for identification of the unknown, and that can be established with other positive spectroscopy identification like infrared, in order to confirm, or even the mass spectra to confirm the identity of the species. In quantitative analysis, what is often used are the peak heights and peak area. The quantitative column is based on the comparison of either the peak height or the peak area of the analyte, and through the comparison with the standards. For planar chromatography, the area covered by the separation species served as the analytical parameter. If the conditions are properly controlled, these parameters can vary linearly with concentration. So analysis based on peak height. This can be measured, the height of the chromatograph is obtained connecting the baselines on either sides of the peak by a straight line and measuring the perpendicular distance. Now this is often done in the early days, but now most of the analysis use the peak area. The area is often a lot more reliable compared to the peak height. Yeah, so I highlighted this statement here. The peak area is often more reliable. And in the analysis, usually you have to prepare a set of standards and run through the standards, and then prepare a calibration plot using the standard. Now, one very common application is the use of internal standard. The internal standard is a sample that is that is not interfering with the analyte, but can be used for comparison. And the ratio of the internal standard response to that of the analyte is a much better reliable data for use in calibration and also in the determination of unknowns. So that brings to an end this lecture on the Introduction to Chromatography, Chapter 26, in the CH 410 Instrumental Methods of Analysis course. Thank you.